but this subnet, the person will be speaking on the representation theory of the algebras.
Thank you. Right. So I'm going to talk about representation theory in general of affine algebras, but in particular, this special world of what's the critical level. So, what are for this? First of all, before I'm getting affine algebras, you have a class of Lie algebras or Kac-Moody Lie algebras. Those are infinite dimensional Lie algebras, but with representation theory very similar to that of semi-simple. So that means, in particular, we have root space decomposition, highest weight representations. Borel-Wade theorem, and even Casimir elements. It's going to be important later, even though not in this form. All right. So this is general Kac-Moody algebra. They are defined in this, like we use the generalize Affine matrix, which is just dropping the requirement that when you decompose it into a diagonal matrix, the other matrix will be called definite. So we don't require that, and that's how we get the initial stuff. So that, so now affine Kac-Moody algebras is a subclass of all Kac-Moody algebras. They are associated each to semi-simple algebras. But for each semi-simple algebra, we'll have an affine Kac-Moody algebra. And the abstract definition that uses just the general theory of Kac-Moody algebras with like a generalized Affine matrix is going to be, if we have G semi-simple, we have Affine matrix like this. And then that is the lambda rank. Then we find the affine paradigm is going to be just adding 0 row and column. So we add in it's 0 and like we add just in it's 0, where A0, 0, that's going to be of course 2, and then the other elements are going to be, so this is going to be minus. So alpha is like a set of simple roots, and then theta is the longest root, and this is the core root corresponding to that. And this is going to be just minus theta like so yeah, so this is the absolute definition. I guess the problem with that is it's not very geometric, so a little bit hard to see where, like general Kac-Moody algebras are a bit hard to know where they come from or what they're related to. The advantage of affine algebra is that they also have another definition, which is more geometric, that is basically going to be almost the loop space of semi-simple algebra. So precisely, we have the semi-simple algebra. Then we define, first of all, we define the loop algebra. So this is going to be just with the vector space, just and we'll throw that. Everything I'm going to still going to be over C. They're going to be kappa in the case, so I just use the for just on this. And so the bracket is going to be, so if I have F and so F, Y is for G. So if I have element X, Y in the algebra and FG some Laurent polynomials, it's going to be F1 and FG. So this is of the Lie algebra of the loop G. And then if we have now, to get the definition of affine algebra, we have kappa, invariant bilinear form of G. We define a central extension associated to this bilinear form. It's going to be the 1. So 1 is just like a notation for a vector. This is going to be the central extension associated with this kappa. And so 1 is going to be central, so bracket width of t is 0. And then we have to write the rest. It's going to be, the first term is going to be the same term as we have for the x1 is g. Then we have an extra term defined by the bilinear form, and which is multiplying the bilinear form by the residue of dg, which is the -1 term in the product of f. So, all right, so this is the definition, and then just a remark, because definition 1, there was only 1, and here we have for any bilinear form, we have the algebra, but so let's say if we define kappa 0 to be, this is the normalized Billion form, and by normalized I mean the required kappa 0 applying theta will be 2, and any other kappa just going to be a scalar multiplication of that. So there is really one-dimensional space of such forms. And in particular, every non-zero k will give us an isomorphic alpha.
Initially, you want any invariant linear form or only general?
Invariant symmetric linear form. I think we need to find that.
It doesn't.
Sorry?
The definition doesn't seem to use it, but I think also for this remark, you don't you need simple rather than semi-simple?
Oh yeah, I guess everything else will be a sum over. Yeah, we'll have sum over of each single component. We'll have. So what's this?
Correct.
The critical level is going to be -1/2 Gillian form. So I guess the main goal of today will be to find the special order of this. So then one last almost last definition related to affine algebras. So smooth okay representation B. Smooth means that for any vector being V, we have and we have a subalgebra of positive loops, and that we want that to be 0 for error larger. And I guess equivalently, we can define U, which is going to be quotient of the entire universal enveloping algebra by requiring one will act by one. I guess which is the main difference between the theory when we regard affine algebras. This is an abstract Kac-Moody algebra, because then we do not specify how like a central element will act, and here we do specify. Say we want it to act by one. Then let's say move reps. I'm going to inside the up modules is the same as discrete. So and discrete you have. So take a completion with respect to the d-adic topology, and then smooth is the same as just a module over the. All right, and then what we want is the description of this algorithm. Here is levels. Sorry?
Let's say smooth. You get the notation, so the same as smooth.
No, this is notation.
Notation.
Notation and
Say this is
of the completion of the enveloping object. I guess I want to say where it's one acts by one. Yeah, and then it is the thing.
But you want to complete with GI code.
Yeah, this is the conclusion of it. Yeah. Yes. And in particular, we want to like explain why this category of models over the critical level is special. All right. So I will start with like a plan of how to describe that. I'm going to start with the finite dimensional analog of everything and what we are trying to do.
Sorry, can I just make one comment? I think that the two definitions they do give slightly different results, right? I mean, you can kind of massage the first one into the second somehow, but it's not as though they produce exactly the same Lie algebra, right?
Yeah, like here with our category of models, we're going to have the central element act just by one, and I guess that's the main difference. In the first definition, there is no there's no critical level.
Well, I mean, you have the kind of boldface one will appear with the first definition, but I guess there's sort of two differences. One is that in the first definition, you get something that only involves Laurent polynomials, right? There's no Laurent series. And like by definition, it's going to be of a countable dimension, so it'll look like Laurent polynomials. But then when you impose smoothness, I guess it's sort of the same representations. And the other thing is in the first, if you do this presentation using a kind of Cartan matrix, then you'll also get the Sugawara operator will appear, which doesn't appear in the second definition, right? So.
Yeah. Okay. Yeah. All right. So I mentioned first of all, I'm going to talk about center. So if we have the linear category or we define the center of C, the homomorphism, the identity functor. And this is a commutative algebra. So the main idea is to think about C as something over spec this functor. And what that means is if we have an ideal of this commutative algebra, we can define CI be this full subcategory and by object where the action of the center factors root the quotient. So for example, if this is a maximal ideal, then this would be like base. So, example, talk about if C is modules over some algebra, then we have a map here to just center of A given by the restriction. This is in fact an isomorphism. Nothing the Algebras will be this A acts on everything. So division by an element in the center will be an endomorphism of any other object. So yeah. Okay. So and in our case, what we're going to use is A, which is the enveloping algebra of G. So in that case, so we are interested in the center of the enveloping algebra and then how it will decompose the category of modules over G. So we have the Harish-Chandra homomorphism describes the center, and this is going to be So this is the substance of U of G. This will map to Borel to just H, and here inside of that we'll have just U of H, and inside of that, I mean, this is abelian, so U of H is the symmetric algebra, and we have invariance under the action of the while group, and this is an isomorphism. So now, how is that used for the composition of the category? Well, maybe I didn't mention it before, but so we have, first of all, we have an action of the group. So yeah, if the G is only a Lie group, say C equals Lie group, and then here the Lie algebra, and the Borel shows the Borel subgroup, then G will act on category of G modules over the Lie algebra. And then we can take 6 points by the action. So we'll have rep G will be integrable modules. So 6 points is the same as integrability. So this will be the simplex category. Then we have in between a category where like integrable with respect to the Borel, and then that's it inside the entire category. So this category of representation, this is the easiest. This is a semi-simple category with simple object, just the like integrable highest weight modules. Sorry. This is let's say simple object are P lambda. Well, that is dominant weight. So it's that example of category of equivalent to category of vector space. So first goal is to show, okay, so this category decomposed based on high dominant weights. So what about this category? And here I'm going to use the
What's the meaning of this category in that case?
I'm going to get to that in a second. Okay.
Everyone's now awake.
Anyway, yeah, I mean, for just a category of zero, we don't need anything about the center. The composition is easier. But it will show up not in, like, so here I wrote, I guess, be integrable, but actually say I'm original. So it's category O. So what kind of O, which is we want that we want integrability and takes input. It is an integrable, so fixed point by the uniprooted ideal. So that means like the subcategory where H acts simply. So I guess basic result of representation theory is that O will decompose the direct sum over so for each weight, I can define I is going to be a map from the of G is isomorphism U of H W, and that is H by U of H. Now I can apply lambda. So for each lambda, I can define a character of the center. So it's going to be an element, let's say, so it's within. So this was an element of H star, but of course everything is invariant under the action of W. So project that into the quotient by W, and this is denoted by pi, then can be regarded as an element of this quotient. Very good. Here I'm category O is going to be just direct sum over. So I mean, this is a map to C, so you can regard it as a maximal ideal. So the center, and that will decompose into this subcategory. So this is the point. So here, the structure of that is like a scheme is very boring because everything will just be like decomposed like over direct sum over what seeds over closed points. It will be more interesting in the Affine. And the description of each those categories depends on the I guess equivalence class of the weight. So if pi is this is the singular case where if this is the image of minus half sum of all simple roots, then this is generated by the Fermat module associated with this weight. This is a fixed point by the action of W. So just one copy of the category of vector spaces. If this is the image of something which is dominant and anti-dominant, so basically all of the components are irrational, then this will decompose as direct sum of the Fermat module generated by by the orbit of the wild group. So it's like W copies of vector spaces. And then the, I guess, complicated case, I mean, yeah, complicated would be if this can be written as the image of an integral dominant. So, and if it's dominant and integral, then there will necessarily be non-trivial extensions between different Fermat modules. Fermat module associated to one element in the orbit, and the Fermat module associated to another element. So, and then of course we can have some components dominant and anti-dominant, some components not, and it will just be each component will behave.
Sorry, I think the way that you defined like C sub I is not quite right for the what you want for this block decomposition, right? Because you don't actually want the center to act kind of strictly through chi. You want it to act through sort of a power of the maximal ideal, right?
Oh,
so it's generalized central character.
Yeah.
Why would the family over some?
So I get, yeah, that's like the power of. Yeah, something like that.
Okay, so divide with the family is the height of the family vector is over some. Ideal should be like objects which have some power. So the motion.
So it's like what states over. So yeah, I can
Like the power.
Like yeah.
Is it
Over-
like a general construction?
For I mean for linear categories.
Family of yes, please.
Yeah, no statement in strength of look that is I haven't seen it. I mean it will be important for us for Affine. I guess there will be like sub schemes that are more interesting than points or powers of points like neighborhoods of points. So here it is now. All right, and then I guess one last thing we want to relate to fundamental case is the flag variety, which is how we can construct elements in each of those categories. So we have the action of G on quotient, and then the flag variety, sorry, is a map E to vector fields on the flag variety, and then for if we take on that dominant integral, we can write a central extension of GB, and then in the middle we'll have twisted differential operators, and it will have again the 0. I mean, I wrote something just that I'm going to use. We can consult for anyway, that will give us, so here we have a map of G to vec, and each choice of lambda on one hand will give us central extension like that, with like twisted differential operators, and on the other hand we can say that like the enveloping algebra related to this general, I don't know, this character. So we have like this lambda give us a map from center to C. So we take this center, so basically say the center will act by that, and this will map into like the algebra of twisted differential operators on phi. And I mean, like extend it to a map. It is a map here. And from that, so if we have a map between two algebras, we get a map between category of modules. So this is so this is literally, yeah, this is the no, I didn't add the definition. Okay, this is that. So this will give us a map to with the D modules on the flag variety, and this is called the localization factor. We'll have a map in the opposite direction given by global sections, and theorem, which is given some interesting localization, that this is an isomorph with inverse given by. So in particular now, so we have a map global section in the opposite direction, and that will induce, if we add, it's like, so we have an action of the Borel on both this side and on this side, and we take fixed point by the action of the Borel. That will map to. So now, yeah, now we get literally this block of category O. So if we have a B variant D module, twisted D module on the flag variety, we get an element in this block of category O. So the example of such an element.
Sorry, just quickly for Valence and Bernstein localization, you need lambda to be regular, right?
Oh.
And then the other thing is you don't quite get a block of category O, right? Exactly because of this strict versus generalized central character business. So it's kind of like category O, but it's strict central character, so it's something a bit. So you can you can do something where you take like a version of twisted differential operators kind of with generalized monodromy lambda or something like that to get category O on the nose.
Yeah, okay, but I mean, it will be inside this block, even if it won't be. Yeah, sorry, I guess what I need is the opposite direction. So with that, I just need to construct elements that not here. Yeah, I mean here, I mean the image will be inside the block, right? Even if
it won't contain like a for example a dominant verma, right? Because those things like never have strict central character.
Oh, thanks.
I mean, it's correct as stated as long as you understand it's strict central character, so it's not really a block of category O.
Yeah. Okay. All right. So. I don't know. I don't have any other notation. Okay, close. Okay. Wait, sorry. Here, so you just this here, like you force the standard to act by this standard.
But how does it depend on the choice of operator?
Oh, and the choice of I mean, I guess, yeah, like, I mean, choice of age, like you identify the center with age, that kind of thing. Like with invariance under W, so.
You can define age without choice.
Oh, that's true. And I don't know. All right, so yeah, example of satisfaction. So we need the invariant models on the by variety. So if we take a Schubert sound, the flat variety, then this in particular is going to be the invariant. So if you take functions on that, there will be the invariant. So a delta function on this cell, which you can push forward of the inclusion of functions on this cell by the inclusion into the function on this cell. This is going to be an element. Means the model forward of B, and the global section of that is going to, it's like, I don't know, I think it's the models. It was should category of in the air. And I guess, for example, to take like the longest element in wild group, then this is just going to be functions on the opposite important subgroup. So if you like on the gradient Verma module, you take that to be just the identity 1, then this is going to be just a delta function on a single point of the flag variety, and this is better. So an element in the category with partial integrability conditions, if we have a delta function, there will give us like function related to Verma. And then for other Schubert, we'll get other, I don't know, a good description. I mean, I'm sure that it's and then if we take, instead of just the integrable, now if we take the modules, these are the modules on G, which are G invariant. That is supposed to give us representations of the group G. And if we integrate, and indeed, in that case, so if this is integral, then we should depend the operators, but just the operators on the line bundle corresponding to this. Yeah, well, I guess I'm now also. I mean, yeah. Let's say the case where, like for general lambda unit parables. So then we have an element, so the dualizing sheet of G mod B, then there is line bundle is an example of element here. And we have, so now we're taking global seconds. Dualizing sheet by so this is gonna be that, and this is by Boyle-Weybach. This is concentrated in degree 0, and is exactly the integrable representation associated to this dominant weight. Yeah. Okay, so this is all I wanted to say about the finite. Any questions? Correction.
Sorry, I said something wrong. I didn't mean the Verma modules do have strict central character, of course, like as your example shows, it's other objects of category O that may not.
Yeah, I was wondering. So what is the object that is not there?
So for example, take in the regular block for SL2, right? There are two simple objects. There's sort of the one with there's like L0 and L-2, right? And the standard is an extension of L0 by L-2, but there's also an extension of L-2 by the standard. So it has three simples in its composition series. It goes like L-2, L0, L-2, and it's the, if you like, it's the projective cover of L-2 or the injective hull equivalently. And that thing doesn't have strict central character.
All right, thank you. Okay, so now to the affine case. So vacuum, integral representation. So vacuum and integral representations of the affine case. So we want, basically the goal is, no, I'm not able to do it. Like that's, I guess, part of that is going to be the next talk. But we want to generalize that affine. So I guess to begin with, we have to choose, like, so we need to choose a slack variety. So we need to choose a Borel. So what's going to be affine Borel? So in contrast with the finite dimensional case where there was basically one choice, I mean, up to conjugation and up to blah, there is basically one choice. Here, there are going to be more than one. So in particular, for example, GO is going to be one such choice. Another choice is going to be the opposite to that. They are not going to be isomorphic. And inverse, and another one is going to be your Harish subgroup, which is valuation of 0-3 image of the Borel inside. So we have an evaluation from G of O to G of G, and we take the pre-image of the Borel. So each one of them will give like different object, different Fermat models. So this one will give, well, I guess, begin with Y modules, which is this one will give the control gradient. So in particular, it's not going to be on, like in the previous case, in the final case, they were on the same slide variety. It's not the case anymore. And those is semi-infinite objects that I'm absolutely not going to talk about. They produce like Wakimoto models. And I guess this is the most difficult, which is why I put number.
Aren't the semi-infinite ones though? Don't they come from like n of k t of O?
Oh. Well, yeah, I mean,
I think that for both I and G of O, I think they're called Weil modules, but the semi-infinite thing, like the Wakimoto modules, are sort of Fermat modules for n of k t of O.
anyway, regardless of which one, I'm not going to talk about both. All right, so yeah, I'm going to talk about is easiest choice G of O. So in that case, what is the flag variety? Corresponding flag variety is going to be the Affine Riemannian. I guess it's not exactly a Borel, it's more like a maximal parabol. So in that case, okay, what we do have, so we have a global section control. Not the model, but like it's not flat section, just global sections from the twisted D modules fixed by kappa on the group of G. Who a mod. So we do have a factor. Well, it's not like a result like we had like inversion where we actually got an equivalence between subcategories of those two categories is not going to happen here. Like there are more involved results.
That's beside there are some finite conditions.
Sorry?
That's beside there are some finite conditions.
I mean, so now you can add the integral is like the
No, but
what is that?
not a good factor. Fine. Shouldn't there be some finite conditions? Maybe you want to say right away that they you
Why can you
no, but the right hand side there are minus conditions, meaning a smoother condition.
Oh, what will
The left hand side there's no condition.
Yes,
Maybe it's much of that side.
I don't know how to explain why. I'm pretty sure it is automatic, but that's
Sorry, what finiteness conditions? There's no finiteness conditions on either side, right?
so the right hand side, just like we wanted smooth representation. So like
But they'll automatically this will automatically land in smooth representations.
Oh, okay.
Yeah.
So yeah, so we get them out from that. This is like the spherical, like there's something category. I don't remember that Erin talked about 2 weeks ago. Not important for now. I mean, I guess it's important for the proof of things I'm gonna say, but not for things I'm gonna say. So we get them out like that. So in particular, we can get our first object on the right hand side. So this is the vacuum into this kappa. This is global section of so we have here an object. Delta of the trivial, like delta of the trivial and bundle. It's definitely an element here. And this is so this is going to be the vacuum representation explicitly. Right, it was like the induced representation from with loops of G one G of just C. So we let like positive loop act like so they act by 0. And this one will act by 1 because of course we need this to act by 1. And then we check the induced representation to G hat. So this is explicit description. Anyway, Oh, yeah, yes. Like, so this was one example, easily like the same construction, we can actually construct all Y modules. So if we replace here C by another like integral representation of just G, we will get general like Y module associated to this finite representation. But anyway, I'm just not talking about they're not going to be important for this. So now what about integrable representation? So just like we did in the finite dimensional case, we want to take like objects that are GK variant here.
Without the X,
Sorry?
plus X or without the by sending it to 0.
So this will act, so G will act like the original action, and then all the positive loops will act by 0, and this one will act by 1. So here it acted by 0 just to start with the trigger. So representations. So I guess we have similar to the flag variety, the card of that is the of 1, let's say. So if our kappa is like positive integer times kappa 0, so I mean, there's not going to be any distinction between kappa and k, but anyway. So this is like positive integer. In that case, just as before, so twist the differential operators and differential operators on this line bundle. This is k now. And we can define the integrable quotient as double section onion of O of k for the dualizing sheet, which again for the duality or something is this double section. And we have a similar railway bot theorem. Is that this is concentrated in degree 0. So one analogy to the finite case, and it's also it is a maximal quotient of impacting representation. So you can explicitly write a sub-representation, and the quotient is going to be the integral representation. So I guess I'm going to say this is an element. But okay, maybe I will say one more thing. So just a remark, in a similar way, and we can construct integral quotient of every like dominant integral weight corresponding to the Y module, like integral quotient of Y modules. And this gives us and I don't know, theorem or something. We have a fully faithful embedding. Sorry, this is not true for any lambda. So there is a conditional lambda, which is that if you apply it to the co-root associated to the highest root, to be less or equal than the level. And then In that case, need a last.
Right in front of you. That's the eraser. Your hand was just on it.
What?
Really near the eraser, or
Yeah.
it's right there. Your hand.
Oh. That's what. Oh, this is the eraser. Oh my God. Okay.
Does this all the time too.
Then fully faithful betting in takeable representations into just representation of G, sending the to the lambda. So in particular, the left-hand side is a semi-simple category, even easier than a representative of G. There are only finitely many simple objects. But that's basically going to be the last thing, which is easy, the representation of affine objects. All right.
So, sorry, I may have missed it. There's some positivity condition on K, right?
Yeah.
Or
So it has to be an integer, positive integer multiplication of kappa C.
positive integer. Okay, yeah, sorry, I just missed that. Yep, good.
Right. All right. So let's take it.
Oh, right.
Right. Let's continue. So we were on a mission to understand the structure of the category of G hat modules of a given level. So in the finite-dimensional case, something that was very helpful was the description of the center. We basically decomposed everything based on the action of the central character, or generalized character. So a helpful thing will be to have a description of the center in the affine case. So that is the fourth part. So let's say in the finite dimensional case, yeah, I guess I didn't write it when I put it there, but let's write it now. So in the finite case, Z of G is isomorphic to U of A equal by W, but like explicit description of that is just a polynomial algebra generated by omega I for I equals 1 all the way to the rank of G. And we even have an explicit description of omega 1 that's universal for any G. This is the Casimir element. So it's going to be half of the sum of the A, where this is basis for G, and J alpha is dual with respect to kappa 0. So this is an explicit description of element in the center. So first, what we want is to have like an affine Casimir element. So how to do that? So here is an attempt that is not going to work. So if we think about J hat as kind of like loop of G, then we can basically try to take the loop of omega 1. So what does that mean? Now there's going to be many, not many, small amounts. So X G, we're going to write X n. We're going to be the element X T to the n, so the element G hat. And then we're going to write X of Z. It's going to be sum over n in C X, and here is in weird mutations from the algebra language. So it's gonna be like a formal power, like a formal power series where the nth coefficient is x to the n. For now, wait, sorry, just one index. In particular, why the minus n minus one instead of n? Because yes,
You take completely unrelated things, right? Different things.
this is like just a formal concept. It's just literally just like this for now. It's staying to the n.
It has nothing to do with like different.
Yeah. Oh yes, yes, it is. They are. Yeah, I mean, I just explain later why we have like C and T. It's actually referring to like two different formal neighborhoods. Anyway, so here is like even tenfold attribute element in the affine case will be, let's take that. And by that I mean, so I mean here we just get like this will just be like a formal power series, and then we want to say that the coefficients of that will be our Casimir element. So I guess we'll get like a family of Casimir elements. Anyway, it's not gonna work, but so then take so, well, the obvious problem with that is that it's not an element of our algebra, not an element at the end of it. Otherwise, in particular, it's not going to be the same. Not the problem. Not that. Why? So, for example, let's take G equals SM2. So omega 1, that's going to be 1 half E x plus E plus H squared. So this one going to be 1 half and E so let's look at this term, for example. So this is going to be sigma n plus n. This is just multiplying E and Fn, and this is E minus n minus 1. And the problem here is that here in the end of the algebra, in the completion of any developing algebra, we can only have n going to infinity. We cannot have n going to minus infinity. We only complete it with respect to the topology. So so one side of the power series is okay, but the other one.
That's the order product.
The what? No, that's the solution will be the order product. Yes. No.
How do you define the multiplication here?
It's like formal multiplication of. I mean, you can work in like a way where you completely both sides.
I think the point is that it doesn't make sense because the point really depends in the terms.
Yeah.
Is it condition?
Yeah, it's not going to be. I mean, you can write symbolically, like in terms of symbols, you can write that. I mean, I guess it will work in some context, but indeed, not. All right. So to define something that actually makes sense, we use the idea of fields, and operator brought back. So the general idea is to think about X, Z as family of operators. So now, before I said it is just going to be, it's just going to be an index. To now realize it not as an index, but as a coordinate. So Z coordinate on either like a curve or just a form of this. So, and then I guess, okay, so I said family of operators. So operators on what? So we want, if we want that to be something that is, if we want Z to be a coordinate on a curve or a form of disk, but we don't want it to depend on the coordinate, so we need those operators to act on something that is invariant under changes. So operators. What? So I mean, it is like so the element are element in G hat. So they are going to act on a module, like on a G hat representation. But we need to choose representations. So we need representation V to be invariant under the morphism of the form of this. So an example of that is going to be like an element in the O. And an example of such an element, which I before, is the vacuum representation. So a vacuum representation is an example of something that is going to be invariant under the action of the homomorphism of the form of this. Proof that this is going to be invariant, for example, I think Aaron showed us that the spherical category is going to be invariant under change of coordinate, and then it's going to be image of golden section. But just in general, elements here are going to be invariant. So of course, you can make other choices of although I can leave you to do this. So we like so yes. Our operators are going to be x of z for are going to be elements of endomorphisms, still linear of the vacuum. Bracket 6. So it's going to be like a power series of operators on this vacuum. And we go, so X is going to be an element in the vacuum. For each element in the vacuum, we're going to have a family of operators. And I guess I didn't define it. Let's say what we want. We want X or any X in the vacuum. And then in the case where for X in G, which is what I started defining before, this is going to correspond to X minus 1, so X and dot V1. So this is what we want to define. So far, I only defined this element, like what are the fields corresponding to element in G. Now I want to define fields corresponding to elements in the vacuum representation. So now I'm going to use the idea of thinking about these operators that are moving along a curve using a coordinate. So if I have given like x, y, and z hat, we can define multiplication. We can write y of w as an element in endomorphisms of the kappa bracket c bracket w, as long as the not equal w. In that case, it does make sense. The problem is, of course, where the 2 points do collide, like when we take the limit as z goes to w. So this is the definition. Yeah, now it's going to be a definition. Field is an element, so it's going to be an element x of z in And in like families of endomorphism of B, but such that so and this is the main axiom for what we're going to call field. Okay, let's say not a field, a collection of fields. And we need fields. So we're going to define some family of operators here, but the property that we need between fields is that for X, the Y, W here, we want the limit of W of X, V, Y, W to decompose into two components. So the first component is going to be what's called the normally ordered product. And the other component is going to be the commutator. So far I just wrote letters, but the main point is that we require that to be the part that is regular with respect to the minus W. And we want to have a decomposition, so the commutator will only be in the singular part. And minus W. So intuitively what it is we have a family of operators that their commutator lives on the diagonal. It will be made precise in the language of chiral algebras. But let's say just for this is the normally ordered product. And this is going to be the chiral brackets. I think that's going to show up. So a corollary of the, I guess part of what I'm going to say. Oh, so now we already have a definition already defined. What is X minus 1 Z for like what is X Z for X in G, and now if we have two of them, so now X, Y of Z is going to be defined as a normally ordered product. So the way to multiply them is to take the normally ordered. So now X, Y is going to be an element of DK. And then inductively, induction for X in D. Okay, so we start by defining fields corresponding to elements in G, and then we extend it inductively to the entire vacuum representation by taking again and again normally ordered products. And then I guess just one important property, the most important property, I guess, that is a consequence of this axiom, it's like called the locality axiom, is going to be that now computing commutators is going to be very easy. And the reason it's going to be easier. The reason it's going to be easier is because we already know that the commutator is only going to be in the singular part. I'm not going to actually prove it, but I'm just going to like it. So
Sorry, here should C equal W right inside of it.
this is supposed to be, yeah, yeah. W. Thank you. So for X, Y, A, we have the following formula for the commutator. The sum over n greater or equal to 0 of the n. So if you remember, a field is going to be like a power series. So it's going to be a power series. So you take the nth coefficient of this power series and apply that to y, and then W, and then it will have only powers of C minus W minus n minus 4. So the main point is we only take the main point is that we take only n greater or equal than 0. So we only have the singular part gonna give a contribution, and then we also have a formula for what that is. Maybe I will also write like the so what's the formula that we get for the coefficient? Because I'm talking about like field, but the main point will be to then take the coefficients, because those are going to be actually operators and not a family of operators. So the commutator relation for the coefficients is going to be, let's say, so, and choose and y, and then okay, a formula. But the main point of that is this actually defines a Lie algebra structure on what I'm going to call L. Actually, it's a Lie algebra attached with the vacuum representation, which is going to be basically the span of symbols of the form A and for A, V, K, and N is Z. So, and okay, so this is just a definition of Lie algebra, but it is compatible with the one for the enveloping algebra. And what do I mean by that? So there is a V algebra homomorphism between, well, the completion of this Lie algebra and the completed enveloping. So this is not going to be an associative algebra, so but we will have a map of the algebra here. You forget the associative algebra structure on the right hand side and you disregard the algebra. And I guess this is the reason why we can extract information about the enveloping algebra from those fields, because we can define commutator that is compatible. Then finally, third, so we can also define, so what we're looking for is the center of that, but we can actually define a center for that. And it's going to be important to definition. The center will be Z of I G hat is the center, like endomorphisms of the vacuum that are G hat linear, which is by definition, because this is like a free, like just by definition of that is like an induced representation in the thing, and there's the kappa invariance under the absolute positive. So, well, later we'll see that actually for kappa, which is not critical, is going to be 0. So, and then we're going to drop the kappa, and it's going to be related to the Z that I don't know who mentioned it. Someone mentioned. It was a week ago. Anyway, this is going to be the same thing. But yeah, okay. But what we do, so what we so far have is like, so we have a map. If we have a center of the entire thing, we're gonna be able to I don't think we have anyway. So we'll start, the plan is to start like constructing an element like a category element in this center, and then explain why it's actually going to be an element of the entire center. Then show that this will actually come. So this definition finally is Segal-Sugawara operator, which is
silly question. Why is the kappa subscript on the Z and not the D?
No reason. I mean, I guess here because so it started with A the C because we had this enveloping algebra, and it's not the enveloping algebra of G of K. It's a quotient of that where we made one, and then this is going to be a sub something of that. So we just do the same here.
Thank you.
Nothing bigger than that. All right, so so the definition is going to be almost logical. This is going to be, so we are going to define a field, and this is literally going to be a field corresponding to the Casimir element. So we already have a definition of a field for any element in the enveloping, in the vacuum. And in particular, we have a field corresponding to that. So the definition would be 1/2 sum over A of the normally ordered product of those fields. So almost the same as the first attempt, but we now take the correct product of fields, which is the normally ordered product. For example, if we take G equals SL2, then if you remember, we had a problem with the, for example, with the first term. So now the normally ordered product of EBZ SD is sum over n plus n equals n less than 0. And again, plus n plus n 0 and n. So all that happened here is that okay, it was okay. Oh no, it was. So it's okay to have an infinite like part series as long as n is going to infinity, because that's the direction where we do complete. And then what we do for the other half, we just switch the order. That's why it's called normally ordered product. Which was actually defined before. There was like the point of view of field, and it was just let's make things work.
So that these Z kappas are a quantization of the Z's are.
No. So
Yeah, the C's are substitutions,
position, and this is against the main point of this entire half. What is the commutator between the field corresponding to the basic element of G and our operator? Oh, I guess before I'm even saying that. Okay, no, I will say after. So this is going to be kappa minus kappa of critical level over kappa of 0. A W the minus W minus. So here we see for the first time like the difference between like normally ordered and between critical level and general level. So for critical level, we get that the commutator is 0. So it's going to be a standard element because it's going to commute with any basis element. So proof. So we have a formula, yeah, here for how to take commutator of field. This is the main reason why we need the language of field, because allow to compute commutators. So first of all, this is the definition of it. Like it's going to be sum n greater than 0 a b dot omega 1, just the usual Casimir element minus n minus 1. Okay, so first of all, we sum only over n greater or equal than 0. And the main observation is that, okay, this is of degree 2. And those operators will like operator of degree n will shift the degree minus, sorry. And any operator of degree n will shift the degree by n. So this is 0 for any n greater than 2. So we only have to compute n equals 0, n equals 1, n equals 2. So instead of computing many commutators, we just have to compute 1. So I'm going to do 2 of them. So start with n equals 2. In that case, what we have to write right now, I won't get confused. So j to b, then I have to multiply by this Casimir element. If you remember, we identified between elements in G and elements in the T inverse time G. And then and now, okay, so the idea is just to move this element to the right, because we know that in the vacuum representation we only have elements of negative degree. We can only have on the right hand side minus. So this is going to be 1/2 B inverse A B G A minus 1. Then we need to add a commutator. So we need a 1. And then again, move this to the right. So 1/2 C minus 1 A minus 1 G B. Well, this is already 0. We have 2 on the front. So plus the commutator. Then plus this commutator. All right, and then it's equal. So the commutator between 2 and minus 1, if you remember the commutator relation we had, is you take the commutator of J, B, J, A, and then you multiply by the polynomial. This is just the commutator in the loop algebra. Is the extra commutator that we get is in the affine, in the centrally extended one, is when we have here an index and here minus this. So this is going to be J minus 1A, and then commutator of J, B, J, A, and here we have a coefficient of 1. So it's going to be 0, and then plus so again, same thing, J, B, J, A, and tensor T, J, A minus 1. So this element is 0 because we have 1 front. Okay. Yeah. So this is the same as 1, 1. Again.
In both these propositions, there's a W on the right hand side, but no W on the left hand side.
Yeah, because I was kind of cheating. Like basically the commutator is the way it's going to be defined is in terms of delta functions. So supported on the diagonal.
Okay.
Yeah, I mean, the only thing that matters is that, like, what is the coefficient? Like the actual meaning of like the power series, what type of object we are working with, is part of the simulation of vectors operator algebras. And what we're doing is basically saying part of the axiom is that it makes sense. Like, you know, like exchanging between power series in Z, power series in W, and then switching the order, and then just talking about that. So you can just think about it as a formula for the coefficients. Anyway, so finally, this is minus 1/2 sigma of kappa. So now we do have an extra. Yeah, I guess. Yeah, I missed it there. So, no, okay. So we have that, and then we just compute these two. So we get. So here we have index 1, here -1. So now we do get the extra commutator of the affine algebra. So it's going to be kappa of the right hand side. And then kappa is invariant. So same thing as kappa. Okay, this is by definition of invariant polynomial form JA. And this is going to be 0. Why is it going to be 0? Because, for example, like this kappa for independent of a choice of a basis. So you can always choose a basis for J after like the dual, like it's self-dual, like choose an orthogonal basis. So it's going to be 0. And then I'm going to do the computation for n equals 1, but skip some of the equations as thing. So we have A1. So anything again, maybe I would just. Okay, I guess I will just I will skip -1/2 J _J1 A inverse plus commutator JB 0 plus kappa JA. I guess I have to multiply J -1 plus sorry. A inverse and write the final expression. So this is going to be sigma over kappa J E J A minus 1 plus 1/2 A J E J minus. Okay, so that's the result, but
It really is that simple.
what?
It really is that simple.
I mean, I keep three steps. It's really not like you just commute things until you get to the right, and then either get 0 because coefficient was positive, or you
Cancellation.
get something that you can write in terms of complex. So that's the only thing that's happening here. Just exhausting. Anyway, all right. So what is this term? So the first term, this one here, is almost like the decomposition of the vector JA -1 with respect to this basis. With the only difference that the basis that we chose was with respect to kappa 0 and not kappa. So the first term is just going to be kappa over kappa 0. And then the second term, what we have here, this is the adjoint action of the Casimir element. Like just literally by definition, the Casimir element, we have JA and then J lower, so we take commutator as an again commutator. So the Casimir element is the central element, and the killing form is exactly the one where this central element will act by 1. So in general, it's going to be, and then we have 1/2 here. So 1/2 killing form over kappa 0. And this is the same as kappa minus A times A. So this is going to be over kappa 0. So we finally get that we, I mean, yeah, this gives the result. So this is what we want. So it's a commutator that will be 0 for kappa equals kappa C and non-zero otherwise. All right. So now I can already get a result about the case of non-critical level, the center in non-critical level. So for kappa not equal to kappa C, we can define. Oh, so first of all, I mean, maybe let's say for not equal to kappa C, I'm going to define just normalize the coefficient of this operator. So this is just going to be C. The original one, the coefficient in the field corresponding to omega 1. And so we get from the formula there that the commutator between that and the basis elements is going to be minus n, k, and a. Okay, so when you take commutator between that and one of the basis elements, you just get degree times the element. And that's the main point. So in the non-critical level, we have a grading operator. We have a grading operator, and degree 0 element, there is only one degree 0 element, which is the highest weight vector. Then corollary or C or so it's the grading operator. So if it is in the center, we get that. So if we do have, so if I don't know, S is in the center, then the commutator with this element, which is, so this is, first of all, this is the grading operator, so it gives the degree of S, we'll have 0, we will get element of degree 0. But we only have one element of degree 0, so that's the only element in this.
Did you mean like curly C or straight C?
So I went to write this one, and then let's say, in fact, but I'm not going to show how, but you can show that the entire center is also. Yeah. So the relation is going to be that this will correspond to, let's say that, like this will like correspond to like this, and this will correspond to the puncture this. So there will be like an embedding between one and the other. Like in terms of your talk that is going to describe this center as in terms of pairs, this will correspond to pairs on the disk, and this will correspond to pairs on the punctures. But you know, for the critical level, like we can actually write down explicitly like what's the relation between them. I mean, it's going to be a position. One is going to be like yeah.
But that's not right.
Yes, there is. So there is a map from the entire center to this point.
What else is needed to show this?
Okay, so now for critical level. So for position, it's going to be that. Okay, so I guess let's say for G equals SL2. So we already have impedance to prove the case for SL2. For general G, I will say later. So from now on, I will just try is the one. And the reason we're making out the level is because we know that there is only one that is interesting. It's going to be, I move to E and I do X for N less or equal than -2. And the entire center is going to be the 1 and in C. So basically, you can already see here the why I said that one is like this and one is the function this. This is like jet, this is like loop. So one of them we take just the jet of omega one of the Kashmir element, and the other one we take the entire length. And that's basically how the proof works. I'm not gonna write all the details. All right, so we already have a map from that. I will start like with the smaller center. So we already have a map from here to the center, because by this proposition there, we know that all of those elements will commute in the central case. And then what we're doing is showing that it's an isomorphism on the associated graded. So in the associated graded, we will have associated graded of this one is going to be just jet of the center of the original G, which is C of omega 1. So the center for D, so for SL, the center of just SL2, not SL2, not the affine one, is C spanned by the Kashmir element, and the associated gradient of the center of this one is just going to be the jet of that, so we get an isomorphism between them. And proof for the entire center, which is a bit, I mean, also that is not obvious, but I guess for the entire center is a bit more involved, but I guess it's going to be the same. So for so oh damn. I did it right. Anyway, the commutator will like, I mean, so I guess I forgot to say that one thing. I mean, so here I just said for m less or equal than -2, even though the computation was for any m, not just for m less or equal than 2. And the main point is just like for m greater or equal than -1, those will be the zero operators. They will annihilate the highest weight vector. So the commutator is 0, but the operators are also 0. But those operators for n greater or equal than -1 are not 0 for the entire center. So we have a map on those operators to center. And again, we want to show that the associated, we prove that it is an isomorphism on the associated gradient. So that this is basically the loop of center of G. And so omega 1. So it's an isomorphism on the associated gradient. Of course, the proof here is way more complicated because nothing works when we take loop, when we take infinite in both directions. And I don't know, everything becomes complicated. The first case where we only took the infinite, the proof is basically that. And then let's say what is happening for, so that is for SL2 hat. For let's say general G. One can show that like the center is going to be, so smaller center is going to be C spanned by all the coefficients of all the omega in like so. And -2. So the center of G itself was the G was spanned by omega I for article 1 and the rank. So here we will have basically for each one of them, we can define a corresponding field because we know how to define fields for any elements in the vacuum representation. And then we take all the coefficients, and this center is going to be for m less or equal to -2, and the entire center is going to be same thing, but when we take all n. But there is like so for the SL2 case, there is a direct computation. We like a direct proof using computation because we can actually like find what is the expression corresponding to the Kazimir element, and then they compute the relation. For general omega, the proof that this is an isomorphism is indirect. I don't think, at least 15 years ago, there was no known general formula for those elements. I don't know how things are now. And Frankel-Fagan proved that using what they call free field realization, which is like embedding our V, like our vacuum V of K, like our vacuum representation into a bigger, but a bigger like vertex operator algebra corresponding to a commutative Lie algebra, and then doing the computation there and then showing that the center will have to be that. And I think next week, Hariel will show us more geometric. And I think that's what I want to do then.
That's not the right way. Then, small assembly is the quotient of virus. The small assembly is a quotient of virus.
I mean, in this language, not so much. Like, if you do know that those are the elements that will correspond to that, then yes, because that by the same way that you show that those elements are in the center of the smaller one, you get So for computation, you can get that. Conceptually, what you will have to do is to identify that with the space of operators on the disk and the space of operators on the function disk, and then it's just restriction. You have to bundle over the disk to restrict it to functions.
Thank you.